Excellent. So we can begin. Thank you, everyone, for attending our Friday noon talk. Today, we have the pleasure of welcoming Dr. Dimitre Hristov. So let me tell you a bit about him. Dr. Hristov is an associate professor of radiation oncology and medical physics at Stanford University School of Medicine and the program director of the Stanford Medical Physics Residency Program. His research has been focused on the development of novel imaging and image guidance techniques for cancer-related investigations, as well as treatment planning optimization. Previous to that, he was medical physics faculty at McGill and conducted research on freehand 3D ultrasound image guidance for radiotherapy simulation and pre-treatment verification, which resulted in a technology licensed and commercialized by Resonant Medical Incorporated in Montreal, which was later marketed by Elekta. Later on, as a senior physicist with System Concepts and Innovation team at Siemens Oncology, he's contributed to the development of mega-voltage cone beam CT, which has become a commercial product. I'm sure many of you are familiar with it. At Stanford, in collaboration with Philips Ultrasound Investigations, he's conducted research on telerobotic 3D ultrasound for real-time soft tissue guidance concurrent with radiation beam delivery, with some of the resulting technology deployed in several pilot studies on the application of contrast-enhanced 4D ultrasound for cancer therapy monitoring and response assessment. And as well, it's worth mentioning that Dr. Hristov is a former graduate of the MPU program, so he completed both his master's and Ph.D. in the McGill Medical Physics Unit. So we're very glad to have him here today to speak to us. So I'll pass it off to you, Dr. Hristov.
Thank you, Peter, for the introductions, and thank you for inviting me to speak at the MPU seminar. And thank you, everybody, for joining that seminar today. And I'm going to take this opportunity also to advertise that at Stanford we always have medical physics residency positions available. And as I just mentioned to Peter, we've been very happy with the great quality of McGill graduates and Canadian graduates as well. So if you're about to graduate and available in June, I'm inviting you to apply to the Stanford Medical Physics Residency Program. Now, after taking this opportunity to market the program, I'm going to move to my presentation, and I'm going to switch the video because I have to turn away from you. So what I'm going to talk about today is a little outside the field of conventional radiation therapy physics, and I'm going to talk about recent work that we published on dynamic contrast-enhanced ultrasound modeling of a what appears to be an analog to pseudo-diffusivity, which is derived by Intravoxel Incoherent Motion magnetic resonance imaging. And I decided to present that work because it's a very nice example in my mind of collaborative work between radiation physicists, as myself, and then applied mathematicians such as Lauri Mastonen and Sebastian Gottschall from Germany, a statistician, Riv von Euben, and then radiation biologists, effectively as cancer biologist as Ahmed El-Kafas. So let's first start with kind of a schematic representation of the circulatory system. And as we know, as blood oxygenated in the lungs gets pumped by the heart, going through the major vessels, aorta, arteries of each organ, and then as the size of the vessel decreases, going down to arterioles, the blood eventually gets spread into the tissue through the capillaries of each organ. That's where the exchange of oxygen between the blood and tissue occurs. And then the deoxygenated blood gets collected through the venous veins and then going back into the lungs. And what I'm going to talk about today focuses on this region, the capillaries of each organ, where the exchange of oxygen between blood and tissue occurs. And just looking at some of the scales involved in the circulatory system, we basically start with large vessels, with large diameter vessels, such as the aorta arteries, where the blood pressure is high and the velocities are high. And then as we go down to the capillary level, we are now looking at vessels of diameter of 5 micrometers, with very large area, low pressure and low velocity. But that's really the region that we're interested in, because that's where exchange of oxygen between blood and tissue occurs. There are several modalities that are used to sort of image and try to characterize what happens at that level. Namely, these modalities are dynamic contrast enhanced CT and dynamic contrast enhanced MR. And the general idea is that after injection of contrast and dynamic imaging of the contrast propagation, parameters related to imaging parameters that characterize the capillaries on a macroscopic level are derived. And these imaging parameters are the relative blood volume, which is basically the fraction of volume occupied by the blood compartment in a voxel. We're going to use the abbreviation BV for blood volume. It's basically how many milliliters of blood volume you have per 100 milliliters of tissue, and it's sort of measure of the capillary density. The other measure that is of interest is not only how much blood volume the capillaries represent in a given voxel of tissue, but really how much blood flows through that capillary volume per unit time. Because obviously, if you have just stationary blood that doesn't move in time, then there is very little oxygen supply to that volume. And so that measure then becomes the relative blood flow, which is the fractional volume of blood passing through a voxel per unit time. And it's measured in milliliters per minute, which is the blood volume per 100 milliliters of tissue. And these imaging parameters, people have been interested in those for a long time, because there is abundance of literature demonstrating that these measures can be of utility in predicting a tumor response to various type of therapies, or also for prognosis of cancer treatments. So I'm going to show an example of some of our own work. And in this particular example, what we had is we had 23 patients that were imaged both with a PET and dynamic contrast enhanced CT prior to radiation therapy. And then in the mid-course of radiation therapy, these patients also received PET scans and dynamic contrast enhanced CT scans. And from these scans, we derived the standard imaging measures for PET SUV, for dynamic contrast enhanced CT, blood flow and blood volume. And then we looked at what happens to these imaging measures of perfusion, as talking about blood flow and blood volume as a result of chemoradiation. And here we have just two examples. This is an example of the imaging, sort of representative imaging of a patient who eventually responded to therapy and had a complete metabolic response as measured by PET imaging 2 months after radiation therapy. And then these are representative imaging of a non-responder pre-treatment and during treatment. And that non-responder basically had new distant disease at the completion of the therapy as measured with PET 2 months after the completion of therapy. And what you would see is basically that mid-treatment, the PET images demonstrate decreased uptake in both patients. But just visually, with regard to blood flow and especially blood volume, you would see some differences between the responder and non-responder. Namely, if you look at the blood volume, you would see that for the responder, mid-treatment, the blood volume and the blood flow tended to increase, whereas for the non-responder, the blood flow and the blood volume, so you compare this time point, this image to that image, and this image to that image, remained relatively unchanged, at least visually. So we looked at these 23 patients, and what we see here are basically for each patient, we're looking at difference in measures as max SUV, mean SUV, blood flow, blood volume, and permeability at baseline and then mid-treatment. And then in gray, we have people who achieve complete metabolic response at the completion of the treatment. With dotted lines, people whom we could not evaluate because they didn't come up for follow-up imaging, and then people who had patients who had new distant disease. And what you would see is that in general across all patients, the perfusion-related measures such as mean blood flow and mean blood volume, and let's look at the mean blood volume. It basically tended to increase, so the blood volume during treatment appeared higher and was statistically actually higher than the blood volume before treatment across all patients. But when you actually compare the people with new distant disease versus at the completion of the treatment versus patients who actually responded to treatment, you can see obvious difference in trends. So the people who had complete metabolic response, the mean blood volume increased as a result of treatment, whereas people who had new distant disease, the blood volume actually decreased during treatment. And that was statistically significant. And just anecdotally, one of these patients that was not evaluated at the time of our publishing this study actually came up later for follow-up imaging, and we were predicting, this one here, we were predicting that this patient would show up with new distant disease, and unfortunately that was the case, consistent with our predictions. And that little example is just to demonstrate that by imaging perfusion early into the treatment, there is some indications that one could predict the eventual outcome of treatments. And therefore, by doing early imaging and predicting this outcome, one can perhaps early look at alternative treatments or alternative interventions for these patients. Or, if such alternative treatments do not exist, even consider interrupting or stopping the ineffective treatment to prevent toxicity, unnecessary toxicity. All right, so with this, I'm going to move on to the topics of contrast-enhanced ultrasound. And before I go there, one question, of course, will probably spring to mind to everybody is, how come a practicing clinical radiation therapy physicist gets involved with contrast-enhanced ultrasound? Well, the answer is incidentally, and not surprisingly. And actually, it came up from our work on telerobotic ultrasound image guidance for soft tissue guidance during radiation therapy. What we set out initially to do is basically create take advantage of this matrix array transducer, which allows generation of real-time 3D ultrasound volumes. We wanted to take advantage of that transducer available by Philips to create a system that would allow us to do soft tissue guidance and soft tissue monitoring of internal anatomy during radiation therapy. And ambitious as we were, we decided to create a robot that can maintain the probe remotely and monitor the anatomy during treatment. We did design and develop such a robot along with the associated image guidance applications, and we did actually perform a couple of simulations for radiation therapy patients. But as you can see from this picture, we sort of realized that while it was a lot of fun developing the technology and all the visualization around it and localization tools, eventually we come up with a rather big and obtrusive robot that was offering only limited applications of ultrasound in the liver. So that is not to say that this entire work was all waste. We learned a lot. And there are a couple of things that came out of it. Well, the first one was this particular, much simplified version of an arm to hold the probe during treatment. And even though this arm did not get commercialized in radiation therapy, it actually got commercialized by a neurosurgical company to hold surgical instruments during neurosurgery. So that was one positive outcome. But the other interesting outcome was that with this probe and the visualization tools that we developed, we were able actually to translate and use that one for investigating the applications for the contrast-enhanced ultrasound, both in patients and in preclinical imaging. So at Stanford, there are a couple of protocols where the system that we developed is used for patient imaging with contrast-enhanced ultrasound and also for preclinical studies. And later on, I'm going to focus on the preclinical studies, and this work has been published in the papers listed below. So what is contrast-enhanced ultrasound, and how does it work? It basically relies on the injection of microbubbles as a contrast agent, and highlighted here are two FDA-approved ultrasound contrast agents, DEFINITY and SonyView, and the work that I'm going to show you is based on the DEFINITY agent. And so basically what microbubbles are basically little shells, phospholipid shells filled with gas, with a size of 1 to about 3 microns. And if you look at this size, it's 1 to 3 microns, they're small enough to propagate through the capillaries, but too large to actually go out of the capillaries. So this contrast agent is what we call intravascular contrast agent. It always stays into the blood pool, into the blood vessels. The other important thing for the microbubbles is because they basically contain air, they lead to very high echoes when they're insonicated by ultrasound. So in this slide, basically this reiterates this idea. So if you insonicate or irradiate a microbubble with ultrasound, basically the microbubble starts vibrating and scatters ultrasound back, which you detect. But the important thing about the microbubbles is that the scattered signal is not a linear linear signal. In other words, if you irradiate at a given initial frequency f0, you're going to have an entire spectrum of scattered and reflected ultrasound waves with different frequency. And most notably, you're going to have a peak at double the frequency of the initial insonication. So that's another example here of that. The other thing that is important for the microbubbles is that what you could do as well is you could disrupt or you can modify the agent in vivo. So if you, as you start to increase the intensity of the ultrasound with which you irradiate, the microbubbles start vibrating with larger and larger amplitudes. But beyond a certain threshold, you can just destroy them because the bubbles burst, right? So that's another very interesting property, which with some applications, which I'm not going to discuss here, but to put things in perspective, think about dynamic contrast enhanced CT or MR. You cannot manipulate the contrast agent in vivo. You cannot destroy the agent. You cannot clear it. With microbubbles, you can do that. So how do we image? How do we create images of the microbubbles? So here is an example of what we're going to call what it's called the phase inversion imaging, and the idea is very simple. So if you start with the, so we're looking at the if you start with the transmitted ultrasound pulse and you transmit two pulses in a sequence, the red one and the blue one, tissue which basically reflects and scatters ultrasound in linear fashion will basically generate two reflected waves of the same frequency. Whereas the microbubbles will generate reflected waves which have the initial frequency, but they would also have the frequency which is equal to twice the initial frequency. And so if you take two pulses, but you inverse the phase of these two invert the phase of these two pulses by 180 degrees, and if you sum these two pulses, then the tissue signal will be zero because the phases of the reflected ultrasound pulses are opposite. Whereas for the microbubbles, when you take these two pulses and you sum them up, the linear portion is going to cancel, but the nonlinear portion is just going to add up. And so effectively by using two sequences, two pulses with opposite phases, and then summing them up, you can suppress the reflected signal from tissue, and then you can just get the signal from the microbubbles. And there are different variants of this technique. There is also something called power modulation technique, where instead of changing the phase of the pulses, you change the amplitude, and then you do the math accordingly. So here is an example of patient imaging, and I'm just going to go back and scroll a little bit. So initially, when the bubbles are not injected, you can see that with this technique, you basically suppress the tissue signal, so the ultrasound signal is effectively 0. But as the bubbles start flowing in, the linear portion of the signal is canceled, but the nonlinear portion of the signal leads to this contrast-only image of the lesion. In this particular case, this is a colorectal metastasis. So moving on, so how do we do analysis of the contrast enhanced ultrasound? Pretty similar to other contrast enhanced imaging techniques. Basically, there is a bolus injections in a peripheral vein, and then this bolus gets propagated through tissue. In this particular instance here, if you're looking at the liver, leads to lesion enhancement and dynamically over time, as we just saw on the previous slide. And then one would draw a region of interest over a tumor or lesion, look at the time intensity curve, which is the basically mean signal over the region of interest. And then based on this time intensity curve, one can derive different metrics that characterize this time intensity curve. And the common kind of heuristic metrics used for characterization of dynamic contrast enhanced ultrasound studies are, of course, the peak enhancement, the maximum amplitude of the signal, the wash-in time, which is the time from given threshold to the peak of the time intensity curve, wash-in area under the curve here in light blue, which is the area under the curve from the initial starting point, initial threshold to the peak, and so on. So with the system that we had previously developed for ultrasound guidance, there were quite a few. We conducted quite a few studies at Stanford in preclinical models, and so this is basically the setup for this preclinical study. So all the imaging data I'm going to show you later on is acquired with this kind of setup. So we have the mice here under anesthesia, heating pad. The bolus is injected through intravenous access in a tail vein injection. Then on top of the mice have tumors grown on the legs. Between the probe and the leg, we have a vessel containing ultrasound gel, so we can provide acoustic coupling between the tumor and the probe. And the probe, which provides 3D ultrasound images, is basically fixed on the top of this acoustic gel standoff. So here is an example. Here are examples of. So what I'm going to show you here are the time intensity curves from a mouse tumor arising from voxels that are labeled here with the dots with different colors. So you have an understanding and appreciation of what these contrast enhanced ultrasound images look like. This is a 3D rendering, of course. And then if you create the time intensity curves, of the contrast amplitude for these voxel locations here, they're going to look like this. So the blue one will correspond. The blue time intensity curve corresponds to this blue voxel. The green time intensity curve corresponds to the green voxel, and so on. And what I have here in white is also the time intensity curve derived by looking at the mean signal over the entire tumor. So there are a couple of things you will notice. First of all, that if I replay the video again, the signal is quite noisy, and which is also reflected in time intensity curve, and it's a little difficult to get appreciation of what's actually going on. Then the other thing is notably is that even though the signal is quite noisy, when you look at the time intensity curve over the entire tumor volume, it is, despite the noise and despite these fluctuations, which are actually which are actually related to heartbeat, and I'm going to come back to that a little later. The time intensity curve over the entire tumor volume sort of matches what we expect. But the time intensity curves for the individual voxels are nowhere closer to what we would expect for the whole tumor volume. Now, if you filter that data with some spatial and temporal filtering, and basically our temporal filter here was equal to was basically a Gaussian filter with a temporal scale, time scale equal to the time scale of the acquisition, and so these frames are typically acquired with frame rates of 1 to 2 hertz, meaning 1 or 2 volumes per second. So if we filter this data, both temporally and spatially, you can actually appreciate now that there is a much more conspicuous depiction of the blood vessels, but also you can sort of see the underlying dynamics of the contrast propagation in the tumor. And now the interesting observation here is that if you look at the time intensity curves, now that we've removed these high frequency fluctuations related to heartbeat, you would see that yes, the time intensity curve for the entire tumor volume matches what is depicted, what is described in the literature and what we expect. But the time intensity curves for individual voxels are really not resembling this time intensity curve for the entire tumor volume at all. So in conclusion, the intravascular contrast kinetics on a voxel level is considerably more complex than the one on the whole volume level, and doesn't really match the generic shape that we expect for a whole volume contrast kinetics. So we decided to figure out, we decided to create a physical model to model the behavior of this. Let me go back to model the behavior of these time intensity curves. And the model is as follows, right? So if we start with the genetic representation of the tumor vasculature, now we have an imaging system. So the imaging system, of course, is going to blur the vessels, right? And then we have our imaging system or ultrasound, contrast enhanced ultrasound, cannot really distinguish between arterial flow and venous flow. So it not only blurs the images, but it also makes them monochromatic, right? And so to describe the behavior of the contrast in these images, we basically look at propagation of contrast here, a contrast which is a function of spatial location and time, based on some underlying blood velocity field that describes the velocities in of the blood flow in the vessels. But also then we need to describe the propagation of blood in the capillaries, right? And which are completely blurred and basically on a voxel level in the dynamic contrast enhanced ultrasound images. And there has been some work in the MRI literature on that, and one way to describe the propagation of blood in the capillaries is to look at this propagation as sort of a random process where, let's say, a microbubble flows through the capillaries, reaches an intersection or bifurcation, and then it has to decide, does it need to go left or right, right? And then goes either left or right, and then it reaches the next point, and then has to decide whether to go left or right again, and so on. And so this process becomes kind of a pseudo-random walk. And we know that random walks are described by diffusion processes. And so where the diffusion constant describing such diffusion processes is linked to the mean capillary length, the mean length the microbubble has to go between between intersections of capillaries, and then the blood velocity in the capillaries with this expression. So therefore, we introduce also pseudo-diffusion tensor or scalar to describe the propagation of the blood flow into the capillaries. And so with these parameters, the propagation of the contrast basically can be modeled by the following partial differential equation, where the change over time of the contrast in a given voxel, the given spatial location, is governed by convective term, which is related to the concentration gradient and the blood flow velocity in the vessels, and then the gradient of the product of the diffusion coefficient and the concentration gradient. And what I'm going to talk about next is that this diffusion constant here has an analog in what's called Intravoxel Incoherent Motion MRI, and the way the diffusion MRI works, you probably know this already. But basically, if you have two spins, and you apply some gradient during imaging, but because of the gradient, these spins are going to acquire different phase, right? And if these spins do not move in space, if you apply a reverse gradient, you can sort of refocus the spins and get a given signal. But if one of the spins actually diffuses and moves in space, then the subsequent gradient is not going to recover the phase loss between these two spins, and therefore the signal is gonna decrease. And so this can be modeled, and that's the kind of the basic principle of diffusion weighted MRI. But the important thing is that at very low B values, and the B values are basically characterization of how the strength and the time of application of the gradients, of the diffusion preparation gradients, you can actually derive what's called a pseudo-diffusion, which is much larger, a factor of 10 larger than the regular diffusion, which actually, and that pseudo-diffusion, rather than describing the diffusion of water across cells and in the intercellular space, basically describes the collective diffusion of blood through the capillaries. And so in IVM imaging, the idea is that this pseudo-diffusion will be basically the constant that characterizes the collective diffusion of water through the capillary bed. And that should be equivalent, or that's really an analog to the diffusion constant here, which we model with ultrasound, because in both cases we only look for the intravascular motion of the agent. All right, moving on. So this becomes a little heavy here, but how do we solve this equation? I'm not going to go too much into them. I'm just going to give you some ideas of how we approach that. So this is the continuous partial differential equation, and of course, we don't have continuous data. We have samples in space and time. So if we sample this equation in space and time, this is the same equation, but just discretized and sampled in x by y, mx by my by mz voxels, which is our imaging field of view over NT time points. And so to be able to, and our objective here is based on these observations, based on the observations of the contrast, propagation in time and space, we would like to recover the underlying velocities of propagation of blood and also recover the spatial distribution of the pseudo-diffusion coefficient. So we need to estimate these derivatives here of the concentration from the measurement samples. And how do we do that? I'm going to give you an example in 1D. So let's say we have one-dimensional vector of measurements. So here is 1, 2, 3, 3, and 2 with a measurement time interval of tau, right? So simple forward finite difference. The derivative of this vector we can approximate as the just the difference between the subsequent samples divided by the measurement time. This is very trivial, but the important thing is that this finite difference approximation, so our derivative here equals to this vector, 1 over tau 1, 1, 0, minus 1. The most important thing here is that this finite difference can be approximated as a convolution of the initial measurement with a derivative kernel. And the derivative kernel is 1 over tau minus 1 and 1, which does exactly the same operation as the finite difference. Even more important is that this convolution with the derivative kernel can be actually approximated as a multiplication of the initial set of measurements with a derivative matrix. And you can see that the derivative matrix is basically a sparse matrix which has the derivative kernel on its diagonal. All right. So with this, let's look at our equation. So we need to estimate these derivatives from the measurement data. And I just show you that these derivatives can be estimated by convolving the measurement with the derivative kernels. And these derivative kernels, in our case, were basically gradients of a Gaussian. And we are achieving two things here. We are basically smoothing the data because, as I showed you earlier, we need to remove these high frequency fluctuations due to heartbeat, and then that's the smoothing of the Gaussian. And then by taking the derivative, we are taking the derivative of the subsequent of the smoothed concentrations. So to basically these gradients we estimated by convolving with the derivative of the Gaussian here in blue, green, and yellow. Now, the important thing here, however, is that by doing this, we introduce some scale parameters, which are the scale of the derivative kernels in X, in space, and in time. All right, and this is just what I just told you. All right, so then we start with our initial equation. We introduce vectors which represent the samples of the measurements in space and time, and then our unknown parameters are the velocities at each voxel and the diffusion coefficient of pseudo-diffusion coefficient at each voxel. We combine this vector of unknowns in a single vector which has these components, and as I showed you earlier, the derivative operators we can basically approximate as matrices performing multiplication on the unknowns. So with that, from our initial equation, we basically come up with a linear system where we have a matrix A, which is a function of the measurement concentration, and then three parameters. So the three parameters being the spatial scale of the smoothing, the temporal scale of the smoothing, and then the specific form of the implementation of the derivative operators. So this matrix multiplying the vector of unknowns should be equal to the vector that represents the temporal derivatives of the concentration, which also depends on the scales in space and time. And of course, this is to solve this kind of linear systems. Also, you also use a regularizing term, which basically forces the concentration to, which basically forces the unknown vector y to reach zero values, basically go to null in areas where there is no enough measurement data to evaluate the value of the unknowns. And then to solve this linear system, we use the conjugate gradient least squares. There are two benefits of the conjugate gradient least squares. The first one is that it doesn't need explicit representation of this matrix that forms the linear system, because this matrix can be huge given the size of our problem. And then also the conjugate gradient least squares is known to have a regularizing effect of the solution for small number of iterations. So of course, the first thing we did is to try to validate our implementation and whether the inversion technique works. So here I have a synthetic example of 4 boi propagating in space. These boi have different velocities, so 1 millimeter per second and 2 millimeters per second, and then so this domain has 2 velocities, and then it has 2 different diffusivities. So each one of these 4 boi, each one of these 4 boi propagates with a different velocity and in a subspace with a different diffusivity. And then we added some noise. And some blurring to the data to simulate the effect of the ultrasound system. So this is what the simulated data looks like. So you can see the boi propagate with different velocity, and they diffuse at different rates. So this problem in particular has about 500,000 variables, 3.2 million equations, and on a laptop, to perform 100 iterations of the inversion takes about 32 seconds, which is not too bad. All right, so let's look at the results of this validation. So what I'm showing here on the top is the maximum intensity projection through time of the contrast. And the reason I'm showing this is because obviously you can see that in some points of space, you really don't have any, because of the diffusion, the level of the signal of the propagating contrast actually goes below the level of the noise in that space. So realistically, you would not expect to be able to recover the value of the velocity and diffusion in these portions of space. And so to define the region, the spatial region over which we would like to recover the velocity fields and diffusion fields, we basically decided to introduce a sort of arbitrary threshold whereby we only trying to recover the velocities in these areas in space where the contrast, the level of the signal from the contrast exceeds the noise by a factor of 2 throughout time. So at any point of time, the level of the signal should be twice as large as the level of the noise in the particular region. This threshold is somewhat arbitrary, but I think that's kind of commonly accepted. And we are basically saying that we only want to recover the values of the fields in regions where the signal from the contrast exceeds considerably the noise. And so here, basically, what I have on the right is with dotted lines is the ground truth velocities, and then with the the ground truth velocities, and in solid lines black you have the reconstructed velocities along the lines shown here in with the crosshair. Right, so you can see that we have the 4 regions: high velocity, 2 millimeters per second, 1 millimeter per second, and then in this particular one here, you could see that we could not recover the 1 millimeter per second velocity entirely throughout space, but really what we cared about is that region of space outlined in red where the signal exceeded the noise by a factor of 2. So the overall observation is that there is a recovery of the velocities. Of course, it's not ideal, and especially in the regions where you have transition between signal exceeding considerably the noise and then the signal kind of being buried in the noise. And this is the reconstruction of the diffusivities. Again, in the dotted line are the ground truth, and in the solid line we have the reconstructed diffusivities. And what you can see also is that because of the smoothing of the data, we don't have these sharp transitions between regions of the reconstruction versus the ground truth. So with this, as I said earlier, we have we have several parameters that affect the quality of the reconstruction. So let me go back for a second. So these parameters were the spatial scale, the temporal scale, and the for conjugate gradient algorithm, that will be the number of iterations that we need to perform for the reconstruction. So the temporal scale we fixed to be equal to the frame rate of the acquisition, because we don't want to lose any temporal information. So basically, we do not want to have any blurring of the data in time. The temporal scale, sorry, the spatial scale we varied. So the spatial scale we varied from 0.3 millimeter, which is the voxel size of the simulations, to about 1.5 millimeter. And then we also varied the number of iterations and the value of the regularization parameter. And what we looked at is we looked at the mean reconstruction error, which is basically the mean of the relative error of the reconstruction of the velocities and the diffusions. And then we asked the question, what was the value of the regularization parameter and the temporal and the spatial scale that led to the best reconstruction of the velocity and diffusion fields as measured by the mean relative error. And so we can see from this particular graph here that for 100 iterations of the conjugate gradient, using a spatial scale of 0.6 millimeter, which is twice the voxel size, and the value of the regularization parameter of about 0.2, we resulted in the lowest mean relative error. And when we increase the number of iterations to 1,000, the same observation held true again for a spatial scale of twice the voxel size of 0.6 millimeters, and a value of about 0.2 led to the lowest mean relative error, meaning the best reconstruction compared to the ground truth. And then when we started increasing the number of iterations beyond 10 to the third, we didn't really see any significant improvement in the mean relative error. So for the subsequent results, we basically used the 100 iterations because it was the computationally the least expensive, and then our temporal scales were fixed to the frame rate of the acquisition, and the spatial scale was fixed to 0.6 millimeters. So with this, we also performed another validation example where we, instead of 4-bow propagating with linear motion, we had a rotating bolus, so a contrast that is put in a velocity field that causes rotation. And similarly, we demonstrated that the reconstruction technique works, and it can reconstruct reasonably well the velocity fields and match them to the ground truth. So the ground truth, again, the dotted line, and the reconstructed velocity fields in solid. So moving to in vivo results. So here is an example of the reconstructions in a mouse tumor model. So we have the concentration here, just a streamline showing the trajectories of the reconstructed from the velocity fields, the magnitude of the velocity. These are volume renderings, and the spatial distribution of the diffusivity. And there is a negative diffusivity here, which I really like to go back to it if we have enough time, because that's a little bit of a question mark there. And that's another tumor model. Again, the streamlines depicting the velocity fields, the velocity magnitude, and the volumetric rendering of diffusivity. So with these reconstructed parameters, we asked basically 3 questions. The first question is, we're looking at the spatially average absolute diffusivity, spatially average meaning average over the tumor volume. We asked 2 questions: is this imaging parameter reproducible? And basically, to do that, in 20 mice, the dynamic contrast enhanced ultrasound acquisition was repeated 15 minutes apart on the same imaging session. but measured by the interclass correlation coefficient, there was excellent reproducibility with the ICC of 0.9, varying between 0.78 and 0.96. The other question we ask is the treatment. In this case, this mouse, the treatment was done with bevacizumab, which is an anti-angiogenic agent. Is treatment causing changes in this particular imaging matrix? And our experimental design was treated and control mice, so treated with bevacizumab, control with saline, imaged on days 0, 1, 3, 7, and 10, 0 baseline, and then receiving treatment or saline after the imaging session on day 0, day 3, and day 7. And then the interesting question also is this imaging matrix correlated to some sort of histological parameters? And for this reason, to sort of look into this for a set of 11 mice, basically we performed imaging and analysis of the spatial average at absolute diffusivity and looked at whether it's in any way correlated to some histology-derived matrix. So what we have here is the representation of the tumor volume for the control and treated mice from day 0 to day 10. And what you can see is that the effect of the treatment is clearly pronounced after day 3, because even though there was increase in tumor volume for both treated and control mice, there was a drastic increase in the tumor volume starting from day 1, was drastic rate of increase of the tumor volume starting from day 1 for the control mice. And then if you look at the other important observation is that visually there wasn't much of a difference between the treated and control mice, even then on day 1. I remember that the treated mice received treatment on day 0, right here. When you look at the mean absolute diffusivity, there was a difference in the trends of the mean absolute diffusivity between control and treated mice, which manifested itself right after the treatment on day 0. So by looking at day 1, you can see that the control mice in the control mice there was relative there was a tendency to increase the mean absolute diffusivity, whereas in the treated mice the mean absolute diffusivity was actually lower than day 0. And then interestingly, when we looked at the mean diffusivity on day 0 across all mice, this was the value that was acquired that we obtained, 0.009 millimeter per square per second. And this is if you compare this to the same tumor model from the literature, values for the IVIM were 0.007 millimeter square per second. So that kind of gives us some confidence that ballpark the parameters that we were deriving with ultrasound are reasonable. So looking back at treatment response, what I showed you on the previous slides, if you look at the tumor volume, the relative changes of the tumor volumes compared to baseline, again, between the control and treated mice, there were no significant differences on day 1, and then the significant difference starts showing up on day 3, 7, and 10. Whereas if you look at the mean relative diffusivity changes of it relative to the baseline, there was a statistically significant difference pronounced and obvious immediately on day 1, indicating that this mean absolute diffusivity is changes of that parameter are sensitive to treatment. And then when we look at the correlation of the mean absolute diffusivity to two histologically derived parameters. One histologically derived parameters is VEGFR2 expression, meaning the expression of these the VEGFR receptor as measured with the VEGFR receptor as average over the tumor volume. There was a correlation of 0.7 statistically significant between the mean absolute diffusivity and these histological parameters, and there was some correlation with the percentage area of blood vessels derived from histology, even though that was not statistically significant. So these findings have sort of these findings have sort of indicative that further work and investigation is necessary to kind of confirm these observations, because of course, admittedly, we have a small sample size, and this data was analyzed retrospectively. So in summary, we have implemented large-scale numerical inversion of fully coupled 4D physical model, the convection diffusion model, to model the intravascular contrast propagation, which we observed with 3D ultrasound. And we demonstrated that the mean absolute diffusivity derived from that model is reproducible with values that are consistent with the MRI literature for this tumor model. In this tumor model, the mean absolute diffusivity is certainly sensitive to anti-angiogenic treatments. And then with a small sample size, with the caution of a small sample size, that parameter appears correlated to some of histological parameters. And for that, I'd like to thank you, and I'm happy to take questions if we have time for that.